In this work, we have studied different notions of approximate tensor decompositions. And what we have shown was that allowing for some approximation error in your tensor decomposition can lead to profound differences in the complexity representing a given tensor. My name is Andreas Klingler. I am a PhD student in theoretical physics at the University of Innsbruck, and this is a joint work together with Andreas Klingler and Tim Netzer. Now, tensors have this very special property that they can be decomposed into a sum of elementary tensors. And one very relevant parameter in this context is the so-called tensor-rank, which can be understood as a measure of complexity representing a given tensor. Now, there is in fact not a unique way to define a tensor decomposition and its corresponding rank. There are in fact many different possibilities to do so. So, for example, many physical systems can be represented very efficiently by reflecting the physical geometry in the arrangement of indices, or by reflecting the symmetries. But if we have given in addition some global notion of positivity in our tensor product space, this usually leads to some additional challenges. Namely, if we want to decompose a positive element in a naive way, this positivity is not reflected in the local elements. So one has to define decompositions with some local certificate of positivity. But this comes with some price usually, namely separations in the corresponding ranks. So let me elaborate on that a little bit more using one very simple but representative example. Let's consider the tensor product space of matrices. And one very relevant notion of positivity in this context is the cone of separable matrices. So a matrix is called separable if it can be written as a tensor decomposition where all its constituents are itself positive semi-definite. So this is in fact an example of a locally positive decomposition. And so we can define its rank as the so-called separable rank. Now, given such a separable matrix, strictly speaking, it's not necessary to decompose it with or into a separable decomposition. We can also decompose it in a more relaxed way, namely without any local constraints. Now, since the relaxed decomposition allows for more freedom in your local matrices, it's obvious that the latter decomposition is usually more efficient than the separable decomposition. But in fact, it has been shown something much stronger, namely that the gap between the rank and the separable rank can be arbitrarily large in general. Now, this behavior appears also in many other contexts and can be seen as a fundamental limitation in representing tensors, on the one hand efficiently and on the other hand with some local certificate of positivity. But in fact, all these separations appear in the exact case. But in most situations, not the exact case is the relevant case, the approximate case is the relevant case. So therefore, our motivation for this work was the question whether these separations also appear in the approximate case. And what we have shown was that many separations disappear in the approximate case. So going back to our example of separable matrices, we have shown that under some reasonable normalization condition, every separable matrix can be approximated such that the separable rank is independent of the dimension. And this in fact closes the gap between rank and separable rank. So our proof methodology does not only work for separable matrices, it works for a much broader range of decompositions. So for example, we have shown that all the separations between different matrix factorizations disappear under some normalization condition. Further, we also have applied our results to different tensor network decompositions, which are very relevant in machine learning and quantum many-body physics. So I hope I have piqued your interest in this topic with this teaser, and I would like, or it would be a pleasure for me if you would take a look into the main talk, where we'll go a little bit more into detail.